Well, good morning, guys. Handout. Good. I haven't been using, but thanks for that. Somebody. Okay, guys. Any questions about the test on Wednesday? Questions? All ready to go on Wednesday? Good to go? How was the alkene able to learn all of its electrical reactions? Yes, an olefin never forgets. Olefin is an old word for alkene. Okay, well, if there are no questions, we'll move ahead to test 3 material. Everybody got to have a golden colored outline. Resonance. 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 A lot of courses cover resonance, week 1, week 2. Test 1, Lewis structures, resonance. I think it's too early to cover resonance at that point. We mentioned resonance along the way a little bit. We did a little resonance for test 2, particularly with the tautomerization mechanism. Okay, that was resonance. In general, our definition of resonance is an alternative Lewis structure, but you're not moving any atoms, only electrons. And if you think about it, you can only move pi electrons, because if you move sigma electrons, well, you're going to be moving atoms, for the most part, maybe not. Only move pi electrons. Resonance is really something fake on the board, but it's real in real life. Let's look at resonance a little more deeper. Intro to resonance. Neutral conjugated alkenes. 2 alkenes here, 2 dienes. We'll be looking at the chemistry of dienes moving forward. Dienes, 2 alkenes. Difference between these two. This is a conjugated diene, this is a non-conjugated diene. Conjugated diene, p orbitals. Test 1, we look at structure, bonding, hybridization, orbitals. And so everybody knows that there's 4 p orbitals here, right? And everybody knows that there's 1 electron in each of these. That's how you make pi bond and pi bond. Right? That's there. You see all this, right? But all 4 of these p orbitals are said to be conjugated. They're all lined up like toy soldiers on adjacent atoms. P orbital, p orbital, p orbital, p orbital. And when we have conjugation like this, these 2 are overlapping to make pi bond, these 2 are overlapping to make pi bond. Well, what about these 2, p orbital number 2 and 3? Are they overlapping? Are they overlapping to make pi bond between carbons 2 and 3? Why not? You say no. Why are these overlapping but these not? Well, they are. Those are overlapping too. All four of them are overlapping. The original structure there with the double bond there and double bond there is no longer fully accurate. It never was. There's lots of structures we look at that are not really accurate because we're not taking into account conjugation and resonance. It means the same thing, conjugation and resonance. They are. But look at this diene. You got pi bond here. That's one electron overlapping, right? That's how you get pi bond, right? And you got you got pi bond here, there. But is there a p orbital in the middle carbon? No. So, are these two p orbitals here interacting? No, they're not. They're too far away. They need to be on adjacent atoms in this course. What we have here is two isolated alkenes, two isolated pi systems. Here the entire system is conjugated. The two enes are conjugated. Here it's two separate enes. They're said to be not conjugated. Conjugation is just lining up the p orbitals. Are these two lined up with that? Well, they're not be lined up, but they're not conjugated because they need to be close enough to overlap. So that's the difference between conjugated and non-conjugated, this simple example. Which one's more stable? They both have two alkenes. Which one's more stable? We have heaps of hydrogenation. Which one of these is more stable? First one, right? Gives off the less heat when hydrogenated. That implies that it had the least amount of heat to begin with. When they're hydrogenated, they're going to the same place. They're both becoming pentane when they're hydrogenated. This one gives off the less heat, means it's more stable. Why is it more stable? Because it's fully conjugated. Conjugation is just a good thing. Why? Because right here we have more bonding. You've got bonding between carbons 2 and 3 that you can't see from this simple structure. There's some pi bonding between carbons 2 and 3. We got to know that. What's another name for resonance? One is pi bonding, or delocalized bonding. We haven't delocalized anything really yet, but pi bonding. You have additional pi bonding between 2 and 3 due to the overlap of the two p orbitals, due to the increased, or the conjugation here. That makes this compound more stable than the isomer, than the constitutional isomer. We see it in the heats of hydrogenation. Conjugated dienes are more stable than non-conjugated dienes. What about accumulated dienes? It's called accumulated. Is it conjugated or not? Good answer. Yes, it's not. Everybody understand why it's not? Let's look at this. Are these two alkenes conjugated? What's the hybridization of the central carbon? There's no tricks. How many regions around the carbon? 2. Hybridization is sp. Yes. How many p orbitals does the central carbon have? That's right. sp carbon has 2 p orbitals. This is August, right? It's all the same. There's no tricks. Yes. Are these two pi bonds conjugated? No. This is a great structural question here. We have carbon, carbon. Yikes! Somebody has put something on this board that will never erase. Yikes. P orbital. What's over here? P orbital? Overlap, overlap. It's like they put Krispy Kreme on it or something. I don't know. It's got gunk on it. There you go. That's over there. How about the other p orbital on this carbon? How is it oriented to the first one I drew? It's perpendicular. You learn in Gen Chem, right? P orbitals orthogonal to each other. Perpendicular. Yes, it's perpendicular. It's coming out at here. The other carbon, thus, the p orbital is also coming out here. These two p orbitals are coming out like this. Okay? Two p orbitals here. Remember my fingers, okay? They're right here. The other two, though, are like this, where this one has two. It has one like this, one like that. You got here, and you got this. Because the middle one has two, and they're perpendicular. The two pi bonds are like this. Are they lined up like toy soldiers like that? No. You got two pi bonds that are perpendicular to each other, and they're not conjugated. I'm not going to try to draw these out. They're not conjugated. It's a simple consideration of everything you should know. That's called cumulated. We're never going to see cumulated again. Quite strange, odd bonding here. But it's very typical. There's no exceptions. There's nothing crazy going on there. It's just not that common. Benzene. Your benzene is your granddaddy of all aromatics. It's a fully conjugated cyclic system. Every carbon has a p orbital. Okay? P orbitals all the way around. They're fully conjugated. We have 6 p orbitals all the way around. There's 4, there's 2 more. They're all lined up. Okay? And that's the definition of aromatic. If you look back on your functional group page, I told you the definition of aromatic. Every atom in the ring has a p orbital. Well, that's a start. But in addition, they all have to be lined up and interacting. Because, again, if you have 2 p orbitals next door like this, they're not interacting. They have to be lined up because they interact side by side. Something like this cannot interact side by side. Okay? So not only do they have to be adjacent on adjacent atoms in this class, they also have to be lined up in the same plane. Okay, that's basically in your intro to your aromatic. Textbook. Everybody have a textbook? I sometimes wonder, for example, in the bromination lab, which I'll return to the lab this week, ask for the mechanism for the bromination of an alkene. And the majority of you did not show a correct mechanism. Missing arrows. But I wonder why, because we went over it in class, it should be in your notes, but also you have a textbook. And I looked in there, and the mechanism is right in the textbook. Okay? So you need to make use of your textbook. I don't know why you would not. But let's move on. Okay. Showing dipolar resonance structures. Conjugated diene. Now, I'm going to tell you this up front, and I'll repeat it at the end. Showing resonance structures of neutral compounds can be a little bit difficult, especially when there's no heteroatoms, which give you polarity. And if we have polarity, we can use the polarity to help guide us towards resonance structures. And if we have charges, like down below, that can help get us doing resonance structures. I'm starting with sort of the most difficult, not in terms of just difficult, but it's just not that intuitive. But it's good to start here, though, because we're going to start with some very sort of theoretical fundamentals. Resonance here. Resonance involves just moving pi electrons. Okay? And a lot of times when we do resonance, it's really just us doing something on our paper. That's called resonance. In real life, the molecule's not really doing anything. Resonance is really a word for us doing something to help us understand something about the molecules. Okay? So when students say, yeah, then the molecule undergoes resonance. Well, no, that's not right. The molecule doesn't do anything regarding resonance. But we have to get to that point. All right? Let's do some resonance on the board. Okay, we can move pi electrons. What if I take these electrons and move them here? And whenever we do resonance on the board, we use our mechanism arrows because we're moving electrons. Just take that, move them here. Hopefully you know that this is going to mean that we get to, we're moving these two electrons out onto the carbon as a lone pair. Now, we're always going to have charge, typically, when we start doing resonance. Very often. Charge of this carbon is now what? Well, you got to know there's one hydrogen there, right? I mean, there's one H there, right? What's the charge here? Now, plus, it's lost a bond. Charge here. There's two H's there, right? I mean, you got to know where H's are at. We haven't added an H or did anything. Have we added any atoms? Have we moved any atoms? All we did was move electrons. Pi electrons. So that's a pi bond. Here we go. And that charge is negative. Okay? Well, guess what? It's just a resonance structure. A resonance structure is an alternative Lewis structure where all you did is move pi electrons. Does everybody agree that's what this is? It's another resonance structure. We just move pi electrons. It's a resonance structure. We always go between resonance structures using a resonance arrow. Double-headed resonance arrow. Not an equilibrium arrow, not something like this. That's equilibrium. Resonance is not equilibrium. Okay, can we do another resonance structure? Well, now we have some charge. And I will certainly kind of focus on charge as we go forward. Charge can help us. How do you stabilize a minus charge? Do you move electrons towards it, or do you want to move electrons away from that area? Do we need to move electrons towards this area? No, that's going to make it worse. How do we stabilize a minus? Thank you. Move it away. Where do you want to move it to? How about if we take these and move them back in here? Well, we're just going this way then, right? We could do that. That just comes here. So I'm not going to do that. How do you stabilize a positive? Move electrons towards it or away? Towards it. Keep on. You can answer all the questions again. Towards it. What electrons can we move towards it? Again, these. But that would just give us back this structure. Can we move some of these? Yes, we can take these and move these over here. I'll call this windshield wiper. Okay? Alright? And windshield wiper. What does that give? That's going to give us another structure. Boom, boom, boom. Didn't do anything there. What's now between carbons 2 and 3? Yes, that's what this arrow means. We're moving that pi bond over. What's now on this carbon? Now positive charge. There's another resonance structure. I'm not going to draw any more. I could forget about these charges and I could polarize this pi bond here. I could just move these electrons and make minus there and plus there. That would give us 4 charges. I'm not going to do that because actually the more charges, worse. Let's just stick with 2 charges. Which structure of the 3 do you like best? If you had this compound in here and you came up with the formula and then you put together a structure that is 4 carbons linearly attached, what would be your favorite structure or your best that you would propose? And say, hey, I think this is the structure. Which one do you like best? 1, 2, or 3? 3. I like 1 the best because there's no charge. Everything's neutral. More bonds. count the number of bonds, this is going to have one more bond. Because when right here, we broke the pi bond. It has one less pi bond. That's a better structure. This is your major resonance structure. And that's why typically when you see this compound drawn, it's drawn like this. There's lots of things we can say. Pulling together the final sort of statement is difficult here. So we're just going to say some things, but as we move along, we'll repeat these things, and hopefully by the end, we'll have sort of a coherent message. One thing we can do here, though, is this is the same compound up here with just another methyl drawn, without the methyl. You remember how we said there's pi bonding between 2 and 3? How about that right there? There's some pi bonding between 2 and 3. Now, we'll talk about true structure. True structure. True structure is a blend of these. Just looking at electrons. Double bond here between 1 and 2. Double bond here between 1 and 2. Only single bond here. The true structure is a blend of these. So, is there a full double bond here? Or does because of this structure contributing, does it make it less of a double bond? Well, you got 2 bonds, and 1. What's the average of 2, 2, and 1? Somewhere less than 2. So the average should be 2. This would also have to be 2. It's less than 2. Now again, it's not perfect, but it's not 1 either because you got 2 double bonds. The true structure is kind of a bond and a half. We're not going to get precise beyond sort of just a bond and a half. How much bonding do we have between carbons 2 and 3? Single, single. But some double. So this makes the average more than a single. It's more than a single. It's 1 plus some more. How much is between the final 2 carbons? 2, double, single, single. So that's somewhere between a double and a single. Again, this is not that intuitive. Charge. What's the average of the charge on the end? Neutral, neutral, positive. What's the average of that? Partial positive. Again, this is really not a good time to be doing this. Partial minus on the end. Minus, minus, partial, or neutral. What are we doing? We're averaging these 3 together. The true structure is an average of these. That'll be called your resonance hybrid. Let's not talk any more about that now. Again, it's difficult with this molecule. Here's something very important though. Let's take stock of what we have here. How many p orbitals are conjugated in this molecule? It's the same molecule above, except it doesn't have the methyl. How many p orbitals are conjugated in this molecule? We drew it above. It's the same molecule, except it doesn't have the methyl. 4. 4, right? Thank you. 4. How many pi electrons in the pi system? We have 4 p orbitals. This is your pi system. 4 p orbitals. How many pi electrons in this system? We drew it above. It just doesn't have the methyl here. 8. No, it's not 8. We drew them up there. I put a dot in each p orbital. How many dots did we put? Yep, 4 pi electrons, right? You should have been able to answer this in August, or really last year. Did we draw it up there? We had 4 p orbitals. We put an electron in each p orbital. For a total of how many electrons? 4? That's it. That's what we drew earlier up there. That's very important for understanding the pi system. Looking at this here, it's just a tough molecule to do resonance with. Tough molecule. Resonance hybrid. I would read about resonance hybrid in your textbook. Resonance hybrid. Because anytime we can do resonance, then we'll move down here. The true structure becomes really not any of these, including not that one, not the beginning one. The true structure is a blend of all of these. And as we move forward, we'll talk about colors. Just like pink is a blend of red and white. Okay? And if I drew red on the board, and then over here I drew something that looked like white, and then I said, hey guys, we used to drawing this like this, but we can also draw it like this. And guess what, guys? The true color is not red. Okay? True structure is more like pink. Are you familiar with pink? Can you imagine what pink looks like? It's hard to draw the pink. The pink would come from sort of combining these together and getting this sort of hybrid-looking structure with partial bonds and partial charges. That's pink. And I can only draw red, white, and maybe there's a third color that comes into the blend. Okay? The true structure is that pink thing that's hard to draw. And at this point, the structure is not red. The color is not red anymore. And it never was. And so we look at this and we got to know it's really pink. But it's hard to draw pink. So we just draw it as red and maybe also draw it as white. Okay, let's look below. We'll do some of the same things. I don't know if I said it before, but that compound's a little hard to work with in terms of resonance. A little easier down here. A little easier down here. Resonance is very important for stabilizing cations and anions. First, cations. How do you stabilize a cation? Move electrons towards it. What electrons can we move towards this cation? Pi electrons. Windshield wiper. Here we go. What does that give? We now have a plus there, a alkene there, and positive here, right? Now have that structure. Can we draw another resonance structure? There are going to be ways to draw resonance structures. One is going to be windshield wiper. Okay? The other is going to be in and out. All right? These are the ways to do resonance structures. There's no other resonance structure here. The only other way I could do is just windshield wiper these back over. That would just take us back here. There's no other resonance structure for stabilizing the positive. What's the true structure here? Well, here it's going to be much easier to do a hybrid. Between carbons 1 and 2 here, single and double. What's the average of a single and double? What's the average of 1 and 2? 1.5, exactly. It's a bond and a half. This is what this means, bond and a half. Over here on the other two carbons, what's an average of 2 and 1? Double bond and single bond. 1.5. The perfect 1.5 on each side. What's the charge on this N carbon? Here it's plus, but here it's neutral. True structure is a blend of these. Just like the true color of red and white is a blend of those, pink. What's the average of 1 and 0? 0.5. Okay, partial plus. What's the average or what's the charge going to be on the N carbon over here? 0 and positive. 1. What's the average? partial plus. There's your hybrid. And in this case, the hybrid is very precise. This is your true structure. Called the resonance hybrid. Right here, what's the bond order between carbons 1 and 2? Bond order is just number of bonds. How many bonds between carbons 1 and 2? 1. How about between carbons 2 and 3? You said 1 and then 2. Okay, thank you. The answer though is you're wrong. That's in this structure. But what we have to do is when we look at this structure, we have to see that structure. Okay? The true bond order of the true structure, the bond order equals 1.5 here and here. That's the true structure. So which interatomic distance is longer, between carbons 1 and 2 or between carbons 2 and 3? They're the same. It's the same exact distance between the two. The structure is no longer real. Whenever you have resonance, your initial structure, any one structure is no longer real. That's not real, that's not real. Two fake representations. The true structure is the blend. But this is a perfect blend because these are really equal. I should have asked you, which one's better? They're just the same. They're equal energy. And so they contribute just as much. True structure. One here. One thing we've done, though, very importantly, is we've delocalized the cation. Here the cation's on the left end, here the cation's on the right end. But we know that neither one is true. In terms of cation, it's partial plus on each end. And a carbon carrying a partial plus is better than a carbon carrying a full plus. So, we look at this cation, we know we can do resonance. Going forward, we may never draw the hybrid, but we know that we can delocalize the cation from this carbon onto the other carbon some. And at the very top, another name for resonance is what? I think it says delocalized bonding. Okay. That's largely referring to charges, delocalizing the charge. One thing we can maybe compare this to, this cation. Which cation is more stable? If I drew these two at the very beginning today, which one is more stable? This one. Because when we look at it, we know that this is not really a carbon with a full plus. This plus is delocalized. What about this plus? Is it delocalized by resonance? Can you do any resonance here? There's no windshield wiper, there's no p orbitals, there's nothing. Let's look at p orbitals. How many p orbitals does this compound have? How many? 3, right? 1, 2, 3. Okay. 2 electrons. What's in this p orbital? It's empty. That's why it's a positive charge. And back in August, you graphed such a cation. And you saw it had an empty p orbital. sp2 with an empty p orbital. sp2, here's your trigonoplanar. 2 H's, trigonoplanar, empty p orbital. Let's talk about the conjugation a little bit. So you have, these are all conjugated. conjugated cation. And only because it's conjugated can we do this on the board. Okay? Talk about the pi system here. How many p orbitals here? 3 p orbitals? How many pi electrons? Pi electrons would be electrons in p orbitals. 2 pi electrons. There's your system. How do we get to resonance structures? One way we theoretically could get there is take your original system. How many electrons we have? 2. Put them in. I can put them here and here. That would make formally a pi bond here and leave this one empty. Well, that's that. On the other hand, I could put maybe 2 here and leave that one empty. Well, that's that structure. I could also do this. I could put 1 here and 1 there and leave that one empty. That would be a resonance structure, but it would be ugly. It would be 1 here, 1 there, and this empty. That's an ugly resonance structure because it would be a diradical. We're not even going to draw that one. On the other hand, look at the compound I drew before. How many p orbitals here if we get rid of this pi bond? It's just 1 p orbital. Okay, it's empty. I mean, you can't do anything. There's no other p orbitals. That's more the theory of resonance. Draw resonance structures here. Here you're going to be able to draw multiple resonance structures. You can draw more. Multiple resonance structures. You can delocalize the positive charge multiple times. The old windshield wiper, pi bond over. What does that do? Okay. Just take this, pull it over here, make pi bond over here, gives that right. Then we can move this one up. Okay. Boom. Yep. And your mechanism arrows guide the way. What next? This is the 6-membered ring, right? Take these and windshield wiper over there. Positive there. And then we can pull these down here. And that's going to give cation back at the original position. Right? So the charge is no longer delocalized. Now, this one and this over here is a little bit different. The pi electrons in the benzene ring have been delocalized. They're in different positions. But in terms of delocalizing the charge, which is often going to be our main emphasis, the charge is not delocalized any more than, or any differently here. Charge can be delocalized a good bit. What's the hybrid going to look like? The hybrid's going to look like this. Partial plus here, partial plus here, partial plus here, and partial plus there. If you could look at this cation, it would look more like this here. Which structure is, which resonance structure would you call major? This is a hybrid. But of the fake ones, which one do you like best? This one here? Why that one?
No, stabilizing the ring seems to be.
Well, that's actually right. We often will look at maybe, well, this is a secondary cation. That's also secondary. They're all secondary cations. The major thing here is the ring. The benzene ring in place, it sort of makes this major. Okay? That would be sort of the major one. Resonance hybrid would look like this. Importantly, this charge can be delocalized onto what carbons? That one, and that one. Question? Well, the last one and this one's kind of the same. I almost didn't draw that last one, but I drew it because the pi bonds here are. Yeah. And that's just like the benzene ring. Benzene ring can be drawn with pi bonds like this, or you can draw the pi bonds the other way. Well, which is it? It's actually both. That's why benzene rings are often drawn with partial bonds all the way around. Because, or you tell me there's no pi overlap here? Oh, there is pi overlap here. There's pi overlap all the way around. And instead of drawing the dots, a lot of times a benzene ring is just drawn with a circle. Okay? I don't like to do this. But that's the only difference between the two on the end. Stabilization by lone pairs. Thus far, all we've moved is pi bonds. Pi bonds. What about lone pairs? How do you stabilize a cation? Move electrons towards it. Do we have any electrons we can move towards it? Yes, in this case we have a lone pair. Stabilization by a lone pair. The lone pair can be moved in. And what does this arrow mean? This does not mean I'm taking the lone pair and moving the lone pair over to the carbon. It means I'm just moving the lone pair in to make a bond. And it's going to be the second bond, so it'll be a pi bond. And we're going to have now a pi bond here. Now what are the charges? One lone pair left on the oxygen, right? Oxygen is now positive. The original carbon, what's its charge? It's neutral. There's one H there, neutral. And there's a resonance structure. What's the hybridization of this oxygen? sp2 with a p orbital, right? Yes, sp2. You have the oxygen. Yeah? What's the hybridization of this carbon? sp2 with a p orbital. Okay? It's empty. That one has a lone pair. Right? These are overlapping. There you go. There's your structure. Right? There's your structure. Or are you telling me that these will not overlap? If there's absolutely no overlap, then let's just call it the original structure. That is, empty p orbital here, lone pair here, but no overlap. Don't overlap. Or do you think that this lone pair is going to be attracted some to the positive? And there will be some overlap. Well, how much overlap? Is it complete overlap? Or is it complete not overlap? Or might it be somewhere in between? You got to keep in mind, how much does oxygen want to move these lone pair in? Freely, or is it a little hesitant? Hesitant because it's very electronegative. It wants to hold on to it. But does it hold on to it completely, or does it share completely? Well, the answer is it's in between. We have resonance structures. The answer is in between. It's sort of a partial overlap. And if it's a partial overlap, what's the charge here? Partial plus. And what's the charge here? Partial plus. And this is the true structure, which is what I showed you here. And I said, how much overlap is here? It's some. These are the two extremes. The true structure is a blend of these. Of the two extremes, which one is best? Which one's major? You might be thinking, why do we even need to consider which one's best if that's the structure? Because that's what we do. We assess which one of these is best. That is, which one of these does the structure look more like? Does it look more like this one or this one? Which one's best? Anybody? Why do you like the first one? That's a good argument. Good argument. Oxygen doesn't like being positive. Any arguments for this one, though?
I like the second one because oxygen can stabilize the positive charge better than the carbon.
Why can't it stabilize positive better? She said it doesn't like being positive. You're saying it likes being positive? What do you say?
Well, he's got some, I don't know.
Did it hydrogen bond?
There's no hydrogen bonding potential here. There's no hydrogen bond donor in this molecule. I mean, if we dissolved it in something, it might fit. This one's major. This would be called minor. Why is this one major? More bonds. Simple as that. Right here, we just made another bond. Bonding a good thing or bad thing? Typically good. More bonds, better. What's another reason this is better? All atoms have octet. Perhaps that's what you're trying to get at, Ian. And the reason oxygen is okay being positive. It has an octet. 2, 4, 6, 8. If oxygen or even fluorine, if it has an octet, it doesn't mind being positive. If it doesn't have an octet, it will hunt you down and make you pay for it. Okay? Over here, the carbon does not have an octet. The hybrid, very generic a little bit, looks more like this guy. Okay? Last thing. The kid, does the kid look more like mom or dad? The kid looks more like mom. Mom's more stable. Okay? Kid looks more like mom. It's a blend, more like mom does, for the reasons stated. Okay, test on Wednesday. Have a good day, guys.